So, in addition to the baryon number, we have another conservation law, which is the conservation of lepton number. So, there are three conservation laws for the lepton number. First is the electron lepton number, denoted by L sub E. Next is the mu1 lepton number, L sub mu, and the tau lepton number, L sub tau. So first, let's ask what is a lepton. So leptons are particles that don't interact by the strong force. So they can only interact by the weak nuclear force. And if in case the lepton has a charge, it can also interact by the electromagnetic force. So that differentiates it from the baryons and the mesons, wherein baryons and mesons interact by the strong force. So there are 6 leptons that we know, and these are the electron, the muon, and the tau. And in addition, we have 3 types of neutrinos, which is the electron neutrino, the muon neutrino, and the tau neutrino. So although these 3 neutrinos are the same, well, they're not the same because electron neutrinos can be observed in beta decays involving electrons, and muon decays involving muons, and same goes for tau decays involving tau particles. So these 6 particles have corresponding antiparticles. So let's first consider a beta minus decay. So in a beta minus decay, or in general in a beta minus or plus decay, electron or positron is emitted together with an electron neutrino or an electron antineutrino. So let's see first this example. So in this first case, in this first beta decay, a neutron is converted to a proton plus an electron and an electron antineutrino. So this beta decay is observed to happen in experiments, whereas this type of beta decay is not observed to happen in experiments, although they don't violate conservation of energy, momentum, angular momentum, charge. This interaction doesn't seem to happen. So that's where lepton number comes in. So the lepton number from the initial state to the final state must be conserved. So in this reaction, the first one, the lepton number is conserved. So let's account the lepton numbers in this reaction. So initially, neutrons in the initial state for a neutron, its lepton number is 0. So our lepton number should be 0 for the initial state and the final state. So the lepton number here initially is 0, and then in the final state we have 0 for proton. For an electron, we have positive 1, and for an electron antineutrino, we have here a minus 1. So here we have minus 1. Sorry. So the initial lepton number is 0. The final lepton number should be also 0, which is in this case 0 plus 1 plus minus 1 from the electron antineutrino. So in the first interaction, the lepton number is conserved. So as we can see in the second reaction, the initial lepton number is also 0 from the neutron. The lepton number of the proton is still 0. The lepton number of the electron is 1. But the lepton number of a muon antineutrino is 0, because it says here uh, electron lepton number for all other particles other than an electron, electron antineutrino, positron, and an uh, electron antineutrino is not 0. So in the second reaction, we have 0, and then in the final state, we have 0 for the proton, plus 1 for the electron, and plus 0 for the muon antineutrino. So in the second interaction, we have not conserved the electron lepton number. So likewise, the electron lepton number, there's also the muon lepton number. So it also accounts for positive 1 for the muon neutrino, and minus 1 for the muon plus and the muon antineutrino, and then 0 muon lepton number for the other particles. So this reaction is possible. This pion plus decays into a muon plus a muon neutrino. So the pion plus has a 0 muon lepton number. So initially it's 0. And for the muon plus, we have minus 1. So the final muon lepton number has minus 1, and then the muon neutrino has positive 1. So in this interaction, the muon lepton number is conserved. So last, we have the tau lepton number, which is designated as positive 1 for the tau and the tau neutrino, minus 1 for the tau plus and the tau antineutrino, and 0 for the other particles.